Welcome to today's explainer. Right now, the entire tech world is grappling with a massive looming hurdle. We call it the AI scaling problem. For years, the dominant strategy in artificial intelligence has been, honestly, pretty brute force. It's basically, if you want a smarter AI, just build a bigger model, train it on mountains of data, throw thousands of unbelievably expensive GPUs at it, and just pay the skyrocketing energy bills. But here's the thing. We're reaching a critical bottleneck. Forcing a single standalone AI model to just get bigger and bigger is becoming incredibly resource intensive, and it's literally pushing the limits of our global hardware and power grids. The returns on just indiscriminately adding more compute, they're starting to seriously diminish. Because of this, the whole field is desperately searching for an elegant, sustainable alternative to just scaling up brute force. Okay, let's dive into this, because this exact question is what brilliant researchers from Sakana AI, the University of Michigan, and the Institute of Science Tokyo's set out to answer. Think about it. Instead of pouring billions of dollars into building one gigantic monolithic supermodel that supposedly knows how to do absolutely everything perfectly, which, spoiler alert, doesn't really exist, what if we took the amazing, highly capable models we already have and just taught them to work together? The researchers are proposing a fascinating macro-level approach here. They want to create an AI ecosystem managed by a specialized, extremely lightweight coordinator. And they call this collaborative system Trinity.
Now, you might be wondering, haven't people tried to combine different models before? Well, yes, they absolutely have, but usually at the micro level. And that involves literally fusing the parameter weights of different models together, almost like trying to stitch a new combined brain together. The problem? It's often entirely impossible. You run into these massive roadblocks right out of the gate, like completely mismatched neural network architectures. You can't just smash two fundamentally different brains together and expect them to, function. Plus, a lot of the world's most powerful models are locked away behind closed APIs. You don't even have access to their weights to fuse them together, even if the math somehow allowed it. So that sets up a very vital need for a macro-level solution. Trinity bypasses all of this messy brain surgery by acting much more like a manager on a factory floor, simply directing independent workers. To act as this factory floor manager, the researchers had to build a specific coordinator. And logically, you'd probably think that managing some of the most complex, unpredictable AI systems on the planet would require a pretty massive brain of its own, right? Well, get ready for this. 20,000. That is the number of learnable parameters Trinity uses to direct massive, multi-billion parameter behemoths like GPT-5 and Gemini 2.5 Pro. Fewer than 20,000 learnable parameters? To put that completely into perspective for you, a typical large language model today has hundreds of billions, sometimes even trillions of parameters. Trinity is astronomically smaller. We're talking a fraction of a percent of the size. Yet it's successfully orchestrating these giant models to solve incredibly complex problems. So it begs the question, how on earth does a manager this tiny effectively direct an entire room full of geniuses? The secret here lies in a really cool concept called hidden states. You see, when you feed a prompt into an AI, right before it spits out the final text that you read on your screen, it creates this internal contextual representation of your input. Trinity uses a compact, pre-trained 0.6 billion parameter model as its base. But here's the genius part. Instead of waiting for this small model to generate its own full text response, which would be super slow and honestly probably not very smart, the tiny Trinity head taps directly into the hidden state of the second-to-last token. By reading this hidden state, our tiny manager instantly reads the room. It grasps the rich semantic context of your query, entirely skipping the computational heavy lifting of generating its own text. It takes that deep context and uses it to make one incredibly crucial decision. Who should I hand this task to, and what specific role should they play? Once Trinity understands the core assignment, it activates its dream team. It selects a massive LLM from its available pool. Maybe that's GPT-5, maybe it's Claude 4 Sonnet, or maybe it's a specialized open source model. It grabs one and assigns it one of 3 highly distinct roles for that specific turn of the conversation. First up is the thinker, whose sole job is to just strategize. Second is the worker, whose job is to get their hands dirty and execute that strategy. And third is the verifier, whose job is to step back, look at the big picture, and evaluate the results. It effectively becomes this cyclical, multi-turn conversation that is entirely managed and dynamically routed by our tiny coordinator. And this brilliantly illustrates how the baton pass works in practice. Let's say a user asks a really complex multi-step math or coding question.
Trinity might first call up a thinker to break that massive problem down into a clear series of high-level subgoals. Once that strategic plan is laid out in the transcript, Trinity calls a worker model to execute the concrete step-by-step problem-solving based exactly on that plan. Finally, Trinity calls in a verifier. The verifier looks at the worker's output and either says, hey, we need to revise this, or looks good, accept. And guys, this is absolutely crucial. The verifier acts as the stopping condition. It's what prevents the AI from falling into one of those endless, computationally expensive hallucination loops. If the verifier accepts the work, boom, the final answer is routed right back to the user.
But here's the million-dollar question. How do you actually train a tiny 20,000 parameter head to make these brilliant managerial decisions in the first place? Traditionally, researchers might lean on reinforcement learning, or RL, to train AI behavior through trial and error. But the researchers found that standard RL actually completely failed here. Why? Because the reward only comes at the very end of a long, complex, multi-turn loop, so the RL gets totally confused. It produces these noisy, high-variance failures because it simply can't figure out which specific decision along the way, like which model choice or which role assignment, actually led to the success or the failure. So instead of RL, the team pivoted. They utilized a highly efficient, super budget-friendly evolutionary strategy known as sep-CMA-ES.
This unique evolutionary training method is, frankly, just fascinating. Instead of relying on the often noisy gradients of reinforcement learning, sep-CMA-ES works by generating a whole population of slightly mutated coordinator policies. Think of it like a survival of the fittest situation. It tests them all and lets the most successful ones survive and recombine. But the real magic under the hood is that it leverages a mathematical geometry called block diagonal separability. Now, in simple terms, this just means the training method can optimize independent blocks of decisions completely separately. It's kind of like being able to tune a car's engine completely separately from its suspension without those specific updates interfering with one another. Because of this isolated optimization, this evolutionary strategy vastly outperformed reinforcement learning and basic random search. And the best part? It did it under the extremely tight compute budgets you face when you're forced to test your policy by pinging expensive, closed API models. Of course, the real proof of all this cool architectural theory is in the real-world performance. The researchers tested Trinity on entirely unseen, out-of-distribution tasks just to see if it could actually generalize without any prior specific training. And wow, these zero-shot transfer results are phenomenal. Just look at the data we've got here. Across high-level math in Amy, complex coding in LiveCodeBench, conversational dialogue in MTBench, and graduate-level reasoning in GPQAD, Trinity beats every single individual top-tier model that it manages. It outperformed Gemini 2.5 Pro, and it outperformed GPT-5. Trinity somehow synthesized the unique capabilities of the entire pool to achieve this emergent performance that fundamentally surpasses what any single constituent model can do on its own. Now, what's really interesting about this slide is the spotlight it puts on Trinity's jaw-dropping performance on LiveCodeBench. This is a benchmark featuring newly released coding questions, which means the models couldn't have possibly memorized the answers in advance. Trinity set a brand new state-of-the-art record here with an 86.2% pass-at-one rate. That means it solved incredibly complex programming problems completely correctly on its very first try 86.2% of the time. It completely trounced Gemini 2.5 Pro at 67.2% and even edged out GPT-5 at 83.8%. And it achieved this utter dominance by dynamically leveraging each model's specific, unique strengths at exactly the right time in the multi-turn conversation. Honestly, it proves definitively that dynamic, well-managed teamwork truly trumps individual brilliance. The researchers summarized the true impact of this brilliantly. They stated that Trinity robustly generalizes to out-of-distribution tasks, effectively offloading complex skill acquisition from the coordinator itself. Really think about the significance of that for a second. A corporate CEO doesn't actually need to know how to write flawless Python code for the company website, right? They just need to hire the absolute best engineer for the job. In the exact same way, the manager, Trinity, doesn't need to know how to do complex graduate-level math itself. It just needs to know exactly who to ask and how to logically structure the workflow. By offloading the actual hard work to the specialists, we prove that we can achieve vastly smarter AI through much better organization, rather than burning endless electricity and compute just to make one single model marginally smarter. Which leaves us with a final, rather provocative thought to chew on. If a tiny 20,000 parameter manager can effectively orchestrate a group of models to literally beat the smartest single AI on the planet,
Are we moving away from the era of the monolithic supermodel? Are we finally entering a new era of the AI ecosystem, where intelligence is defined not by the sheer size of one massive brain, but by the seamless, highly efficient collaboration of many? It is an absolutely fascinating paradigm shift, and Trinity shows us exactly what that specialized, collaborative future might look like. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.